Let's take a look at example B in section 1.8. Find the inverse of f of x equals x squared plus 1 if x is greater than or equal to 0. Remember, to find the inverse, we begin by rewriting the given function as y equals rather than f of x, so we get it out of that functional notation. Remember, next we switch out the x and y. So the y changes to x, and x squared changes to y squared plus 1. And now we'll solve our equation for y. To do that, we would subtract 1 from both sides, keeping in mind that we cannot add and subtract unlike terms. Then how would we isolate y or go from y squared to y to the first? We take the square root of both sides. Remember that when you take the square root of both sides, the opposite side of y becomes plus or minus. So our inverse is either positive or negative the square root of x minus 1, but it's not going to be both positive or negative square root of x minus 1. So how do we know whether we would use the positive or the negative? If we go back up to our function, we were told that f of x equals x squared plus 1 if x is greater than or equal to 0. And remember, if x is greater than or equal to 0, then x is positive. This restriction tells me that I must take only the positive square root of x minus 1 as my inverse function. Had this read x is less than or equal to 0, then I would have selected the negative side for my inverse function. Now I want you to practice verifying. Remember, to verify that two functions are inverses of each other, you plug the inverse into the original function and it should reduce to x. Then you plug the original function into the inverse and it should reduce to x. So pause the screencast, take a moment, and find those compositions and reduce. So when I plugged them into each other, they both reduced to x. So I was able to verify that these are inverse functions of each other. Next, I want you to graph the two functions and verify using your graph. So pause the screencast again and take a moment to sketch the graph of x squared plus 1 when x is greater than or equal to 0 and the square root of x minus 1. Okay, ladies, so let's check out our graphs. X squared plus 1 is a parabola where the vertex shifts up 1, and then I have the square root of x minus 1. Remember, that's a radical function shifted to the right one, and so here it is. And then are they symmetrical across y equals x? And they are. I have the ordered pair 0, 1, so I should also have 1, 0. I have the ordered pair 1, 2, so I should also have 2, 1, and then I could keep checking in that form. So you should now be able to find the inverse function, verify that the functions are inverses, verify that f and f inverse are inverses, and you should be able to verify by graphing. Our second goal is to determine whether functions are one-to-one. So not every function will have an inverse. In order to have an inverse, a function must be something called one-to-one. That is, if f of a is equal to f of b, that implies that a is equal to b. All right, what in the world does that mean? I know that may not make a lot of sense to you at the moment, but it will in a few minutes. It'll make sense to you. Basically, here's what one-to-one means. It tells us that every function has 1x for each y. You already knew that about functions. But then it also has 1y for each x. So there is a one-to-one correspondence from y to x and x to y. Basically, we're saying that neither the x nor the y coordinate can repeat itself. So is there a test to determine if a function is one-to-one? Yes, there is. Of course there is. This is math, right? We have tests for everything. So we would use something called the horizontal line test to determine if a function is one-to-one. I know that you know what the vertical line test is. The vertical line test lets us know whether or not we have a function. The horizontal test helps us to know whether or not that function is a one-to-one function. So let's look at number 1 here. We have the ordered pair 2, 4, 3, 7, and 7, 2. So I could either draw an x and a y axis and plot these points and then do the vertical and horizontal line test, or I can see, is there one x for each y and one y for each x? Let's check that out. 2 corresponds to 4, 3 corresponds to 7, and 7 corresponds to 2. So notice the x value of 2 is never repeated in the x's, the x value of 3 is never repeated in the x's, and the x value of 7 is never repeated in the x's. We could say the same for 4, 7, and 2. So 2, 4, 3, 7, and 7, 2 does represent a one-to-one function. Let's check out number 2, where we will actually use the horizontal line test. Remember, the vertical line test tells us that we have a function. The horizontal line test tells us whether we have a one-to-one function. And in this case, I would say no, it does not pass the horizontal line test because it crosses through our function in 2 places. Therefore, we have an y coordinate that repeats itself. So this is not a one-to-one function. Number 3, if we try the horizontal line test, would we pass or would we fail? And we see that we would pass the horizontal line test. So this is a one-to-one function. Sorry. Okay. Why, again, is it important to know if a function is one-to-one? Because if it is one-to-one, then it has an inverse. So circle of these functions 1, 2, and 3. Which functions do you believe have an inverse? Number 1 does have an inverse, and number 3. How do we know they have inverses? Because they are one-to-one functions. Let's look at example B. How can we determine whether a function has an inverse algebraically rather than the horizontal line test? How can we do that? So we would set f of a equal to f of b and simplify. Now remember, f of a means we're plugging a into our x coordinate and we're plugging b into our x coordinate and setting those functions equal to each other. It would look like this. I want to determine if f of a is equal to f of b. Or I'm setting them equal to each other. I'm performing my test. So that gives me 1 divided by a square equals 1 divided by b squared. So now that we've set these equal to each other, let's see if we can't simplify. I've got 2 fractions equal to one another. I know that I can cross multiply to solve here. So if I cross multiply, I have a squared equals b squared. Let's solve this for a. In order to solve for a, we take the square root of both sides. And when I take the square root of both sides, I come out with a equals positive or negative b. Well, I also know that the square root of a squared can only equal one y coordinate. So if a is my x and b is my y, I have an ordered pair of a, b, and an ordered pair of a, negative b. Well, the a repeats itself. Therefore, this is not a one-to-one function. Had I decided to solve for b rather than a, would I have had the same result? Let's check that out. So a squared equals b squared. Again, we're going to solve for b this time, so we take the square root of both sides, and b is equal to positive or negative a. And we see again that if we wrote an ordered pair, that we would not have a one-to-one correspondence. So this function is not one-to-one, and why is that important to know? If it's not one-to-one, it does not have an inverse. Let's look at number 2. Again, I'm going to set f of a equal to f of b. And if a equals b, then the function is one-to-one. So f of a plus 3 square equals b plus 3 squared. Well, to solve this, we would take the square root of both sides. That looks awful. When we take the square root of a square, those will reduce, and the square root of a square will also reduce. Okay, now remember that we've got plus or minus. And this is where we have to be a little bit savvy. This domain restriction is x is greater than or equal to 3. So does that mean we take the positive values or the negative values? And if you said positive, you would be correct. So we can discard the negatives and now solve. I know that if I subtract 3 from both sides, those 3's will cancel, and we're left with a equals b. If a equals b, then the function is one-to-one, and x plus 3 squared is a one-to-one function. Now, I wonder if you're thinking, Miss Loden, in number 2, the parabola was not one-to-one. How is example 2, which is also a parabola, one-to-one? It's one-to-one because of this restriction, x is greater than or equal to 3. So keep in mind your restrictions. Let's finish up by looking at example C. I want you to use the graph of a one-to-one function to sketch the graph of its inverse. So remember, we talked about ordered pairs and how the ordered pairs of a function, you can swap x and y to give you the ordered pair of the inverse. So let's start with 0, 0. 0, 0, if we switch 0, 0, we still have 0, 0. Same with 1, 1. Same with negative 1, negative 1. So let's move a little bit further away from the origin, and it looks like I have an ordered pair of 2, 4. So the inverse of 2, 4 is 4, 2. I should probably change these colors so we don't. Okay, let's look at negative 2, negative 4. The inverse of negative 2, negative 4 is negative 4, negative 2. And now I think that we have enough points to sketch our inverse function. And remember, we can check to make sure they're inverses by drawing what equation through them? Y equals x. And so if I draw y equals x, it should go directly through the middle, and it does. Ladies, I hope this helps. Thank you for completing your notes before class tomorrow.